Okay, let's go ahead and start on this one. What do we have for a definition for an ionic bond? What is it that you need? What? Okay, that's it. Bond between two ions. You shouldn't. You can't have one with two negatives, right?
Right.
It's inferred, but if you really want to, you could say between a cation and an anion. That's fine. You shouldn't say anything like between a metal and a nonmetal. That's just normally what an ionic bond looks like. And anytime you have a metal and a nonmetal, yes, that's going to be an ionic bond. But there are circumstances where you have positive and negative polyatomic ions with no metal involved. So it just needs to say.
Does it have to say for its final charges?
No, it doesn't, because you could have an ionic bond between two substances that still gives you an ion. All right, so let's go ahead and write up some formulas here. What do we? So I completed a couple. What's important for you is to realize what the charges are of the ions that you're going to put together to make these ionic compounds. So the chlorine and the sulfur, the sulfide are obviously given already, as are the silver and the mercury and the copper and the manganese. And then the other ones you're going to have to remember what they are. So we can make this easy by right off the bat saying that nitrate's got a -1 charge, and the sulfate's got a -2 charge, and the carbonate's got a -2 charge, and the phosphate's got a -3 charge. And then since sodium's a group 1 metal, it's a +1. And ammonium's polyatomic ion has a +1. Calcium's in column 2, so it's a +2. Magnesium's in column 2, so it's a +2. Aluminum is a +3. Potassium is a +, and barium is a +2. Okay. So that first one I have written up there is NaCl. And why is it just one Na and one Cl?
They cancel each other out.
There's one positive charge and there's one negative charge, so they cancel out to form a molecule. So since sodium and silver have the same charge, what happens when they make a molecule with the same ion? Is it going to be any different for the second one?
No,
Why?
because they cancel each other out.
Because it's a +1 charge. And so anything that's got a +1 charge is going to have a 1-to-1 ratio with chloride. So that means this ammonia here also has a +1 charge. So it's going to make a 1-to-1 compound with that. And then the potassium, it's going to be the exact same thing, right? So those ones that we have filled in already look very similar to each other in the fact that the cation and the anion have the exact same ratio of 1-to-1. This is going to hold true for all across the row. So those four that we've already got done, in each of the next columns, it's going to be identical the way that they look. So what is it going to look for sodium with the sulfide?
Na2S.
Na2S. So the sodium's got a +1, so I need two of them to cancel out the sulfide charge. So what's the one below it, the silver sulfide, going to look like? And the ammonium? So it looks the same for each of these, right? Yeah. I just noticed that. Okay. We just want to be clear about the way that I've got ammonium written up there. Let's do this. So it's NH4 2 and then S. So this parentheses refers to the fact that this sulfur that's got the -2 charge is bonded to an NH4 and bonded to an NH4. It is not bonded to an N2H8 with a +2 charge. This thing here doesn't exist. It's two whole separate polyatomic ions. They're the same polyatomic ion, but they are absolutely separate things. And so then that parentheses, what we're saying with this 2 is I've got 2 of those things that are inside of that. So yes, there are 2 nitrogens and 8 hydrogens there, but they are connected in an N with 4 hydrogen manner. Okay, so we've got the nitrate here, and how's that going to look for the sulfur? Or sorry, for the silver. It's got to look the same as the silver does, right? AgNO3, and then NH4 NO3. It's a 1-to-1 ratio, and KNO3. So these rows are looking the same all the way across, simply because their charges are the same, so they're going to have the same ratio. Okay, so let's do the sulfate one. So I've got Na2SO4. Are we good with that? It looks like the sulfur one earlier because they both have a -2 charge. And then the carbonate one's going to look very similar to that, because the sulfate and the carbonate both have a -2 charge. All right, and then the phosphate, Na3PO4. That way we can cancel out the -3 charge on that phosphate. So how's it going to look for the silver, the rest of the row? It's going to look exactly like the sodium right above it, correct? Ag2SO4, Ag2CO3, Ag3PO4. And the ammonium, it's going to be very similar. I need 2 of them. And so I need the parentheses around that. Same thing for the carbonate one here. Oops. And then for the phosphate, we need 3. Okay. How about for the mercury? The next one down. Okay. Is anybody else going to have that same kind of ratio? The one right below it, right? And then the one right below that, because they all 3 of those have a +2 charge. And the one right below that, because there's a calcium with a +2 charge. Oops. So this is CaCl2, MgCl2, and CuCl2. All of them look very basically the same. The charge balance is the same. So we can do that same thing over here. HgS, and it's 1-to-1 because it's +2 and -2, and then CaS, and MgS, and CuS. Okay, and we've got Hg, and then NO3, 2, and Ca, NO3, 2, and Mg, NO3, 2, and Cu, NO3, 2. They're all looking the same because they all have the same charge ratio. HgSO4, HgCO3, and then I need an Hg3PO4, 2. So the reasoning behind that one, how did that happen? So we had mercury with a +2 charge and phosphate, right, with a -3 charge. And so if I have 3 mercuries and 2 phosphates, this here is going to equal a -6, and this here is going to equal a +6, and so then my formula is going to be Hg3PO4 2. Okay. I'm going to move on to the aluminum here. So I've got AlCl3, and I've got Al2S3, and I've got AlNO3, and I've got Al2SO4, 3. I have Al2CO3, 3. And I have AlPO4, since they're both have a magnitude of 3. Okay, the manganese, there really isn't anything more to it, it's just a bigger number. So for this one here, I've got Mn, and then it needs 7 chlorines to cancel that out. And then Mn2S7 will cancel out the manganese with the sulfide. And then MnNO3 7, and then Mn2SO4 7, and Mn2CO3 7. Doesn't really look like a 7. 7. And then MN3PO4 7. The potassium is just going to continue to look exactly like the sodium, silver, ammonium lines, and the barium is going to look just like the mercury 2, calcium, magnesium, and copper 2 lines. So for the ones that we have shaded in above, so column number 1, so we're trying to come up with a name for that. So I've got this mercury and chloride. So it's obviously an ionic compound because there's a metal in it. So what's this guy's name going to be?
Mercury 2 chloride.
Why has it got to be mercury 2 chloride?
Because mercury can have a variable.
Okay. Since mercury can have a variable oxidation state, you have to specify what the oxidation state is. And so in this case, the mercury is going to have a 2 charge because it says it's got a 2 charge. And then that lets the person know that you're not talking about, say, mercury 1. Column number 2, it looks like we have magnesium and sulfur. So it's MgS. And so do I need to say magnesium 2? Why not? It's its only option, right? Magnesium only has a +2 charge, so you don't specify it. Why am I changing these suffixes to "ide" on the anions? Because that's what you do. Because that's what you do. Silver nitrate, is that right? So why is the name for this one silver nitrate, not silver 1 nitrate? It's a transition metal, so why shouldn't I say 1?
That
Silver is one of the few transition metals that doesn't have a variable oxidation state. The only time you don't have a Roman numeral for the metal's charge is if the charge never changes. And it never changes for silver. Silver is either 0 if it's an element, or it's +1 if it's in a compound. So we don't say it, even though it's in the transition metal area. And then it's just nitrate, because you always just say the name of the polyatomic ion regardless of how many of them there are. So number 4, what do we got? Copper 2 sulfate, okay. So CuSO4. So it's copper. So why is it copper 2 sulfate?
Because copper has 2 charges.
Because copper has more than one possibility, right? So then you have to specify. And we know this is copper with a +2 charge because we know that the sulfate's got a -2 charge. And so then that verifies that the copper's charge is +2. That way we've got one of each. And that's how you figure that out. If you're given the formula CuSO4, you don't know what copper's charge is. So you don't look at that charge, but you do know that the sulfate's charge can only be a -2. And if there's one of each of them, then that forces the copper to be the +2 charge. And so that's why you write copper 2. And then what do we got here? Ammonium carbonate. NH4CO3. Oops. 2. Two polyatomic ions, just say their names. You, as the reader of the 2 words ammonium carbonate, are supposed to know that ammonium's positively charged +1 and carbonate's -2. And so when you put them together, you need 2 ammoniums to cancel out the carbonates too. The last one's potassium. Okay. So I've got K3PO4. I'll do that again. So it's just potassium phosphate because the potassium's got a +1 charge and no variability in that. And then the phosphate's got a -3 charge. I just say its name. Do you want to talk about any of these? No?